All right, so we're going to look at the second half of section 6.4 today, and we're starting with example number 4. And it talks about a scaling factor of a map is what it's talking about. So it says, on a city map, a rectangular park has a length of 4 inches on the map, obviously. If the actual length and width of the park are 500 feet and 300 feet respectively, how wide is the park on the map? So as with the earlier examples that you watched the video for, we're always making comparisons. And in every situation, there's more than one comparison being made. So what are things that we're comparing in this example? Length and width. What else? Yeah, the map and the actual size of the park, right? So it doesn't matter which one you decide to be where, but you need to decide one of them is numerator denominator, and the other one is two sides of an equation. So I'm going to go in that order from what you guys said. So this is length and width as fraction pieces, and then we're going to look at the map compared to reality or real life. So we're going to set up a proportion with these sort of labels in mind. So the top left-hand corner is the length on the map. So what does it say the length on the map is? 4 inches? Okay, so we're going to put 4 here. And I'm going to go ahead and put the units in when I begin. As I start working the problem, I'm going to leave the units off because they become very messy. What about, we're going to move across the top, the real length of the park? Yeah, it's 500 feet. How about the width on the map? That's what we don't know, right? That's the unknown. And the width in real life? 300 feet. So part of the reason I like to put the units in as I work is I want to make sure everything's lining up the way that I was expecting and intending them to. And I think it does, right? Looks okay. But in working the problem out, I don't want the units in there. They're going to become a big mess. So we're going to leave them off. And we're going to multiply across our diagonals. So I have 4 times 300, which gives me 1,200. And on the other diagonal, I have the 500 and the x. And then what would I do? Yeah, I'll divide by my 500. And what is 1,200 divided by 500? And it's fine to put it in decimal form because that's how we would probably be measuring things in reality on a 2.4. 2.4 what? Inches. Please make sure you have units on your answers. 2.4 inches. Does that make sense? Do you have a question?
On a test, do you want us to write like length, width?
You don't have to. If you can keep them straight, it's okay. I would encourage you to write more than write less to try to keep them straight just in case you make an error. Yeah. Yes, ma'am.
I just have a question. Why don't you have to change the feet to inches for both of those?
It's a good question, and the reason is because the reality is these are canceling. The comparison's already being made there, so we don't need to. If you changed it, it wouldn't hurt anything. You'd just have a more difficult problem to do. Yeah. All right. Let's look at Kierra and Dora. They have an interesting dilemma that's quite real-lifey, to be honest. Kierra and Dora worked 3.5 and 4.5 hours respectively on a programming project. They were paid $176 total for the project. Because Dora has fairness as one of her strengths, she wants to make sure that each of them are paid according to the time that they each spent. So splitting it half and half, that really is not appropriate. They didn't work the same length of time. The question becomes then how much should each one earn? So what are you seeing being compared? Time? Oops, let me use the darker color. Time compared to money. What else? Yeah, the people, right? I mean, how much each people earns and how much not each people earns, but each person earns and how much each person works. So we have Kierra on one side and Dora on the other. There's one more way you could set this up, and I'll show you how to do that in a little bit, but just as a reference point, we'll start here. Okie dokie then. The time is the easy one, because we know how much, how long each of them worked. How much time did Kierra work? Yeah, 3.5, and you can write it in fractional form or decimal form, whatever works for you. I'm going to go with decimals for the moment. How much time did Dora work? 4.5. The problem is we don't know what either of them should be paid, right? We don't. So how do we deal with that? Well, we know what they should be totally paid combined, right? Combined, they should make 176. Agreed? So I could let Kierra make some unknown value, X. And if I paid Kierra X, how much would I pay Dora? 176 minus X. Just the leftover, right? Whatever remains, that's how much Dora would make. So this is one way to set up the problem, and I'll show you another one later. So we're going to split this apart with a multiplication, right? Cross multiply. The one thing you have to be careful of when you cross multiply from Kierra's 3.5 down to the 176 minus X is that you distribute the 3.5. So I'm going to get 3.5x, but I also have to multiply my 3.5 times the 176. So that's minus x. So what is 3.5 minus 176? Or times? Sorry, Danielle, what'd you say? 616?
Yeah.
Good. So 3.5 times 176 is 616, and then 3.5 times the x is negative 3.5x. And this will equal 4.5x. And then we can add the 4.5x. I don't know why I did that. I meant plus the 3.5. Getting carried away. 3.5x. Okay. So on the left I have the 616. What do I have on the right? 8x. And if I divide by 8, how much money will Kierra make? 77. So Kierra makes 77, and what would Dora make? 99, because that's 176 minus the 77. There is a slightly different, it's not as intuitive way of setting it up, but the mathematics of it works out a little bit simpler. You could compare the time and the money like we did before, but you could compare one of the girls, and I'll just use Kierra since we have her, to the total. So Kierra's part of the problem stays the same. It's still 3.5 over x, okay? But the total amount of time that is worked by Kierra and Dora combined is 8 hours. Right? 3.5 and 4.5. And the total that they make combined is 176. You'll still get 77 in the end. You just don't have to worry about the distribution part of it. So that's another way you could set the problem up if you like that. All right. Let's try another one. At Rattlesnake School, the teacher-student ratio is 1 to 30. If the school has 1,200 students, how many additional teachers must be hired to reduce the ratio to 1 to 25? So, what are the comparisons that are being made? Yep, there's a ratio issue, right? The ratio itself. And I mean this as a ratio. And then the other piece is the actual number. of students and teachers. Are you with me? So what is the ratio currently of teacher-student ratio? What is it now? Yeah, it's 1,200, or I'm sorry, it's 1 to 30, right? So right now I have the teacher on bottom, whatever reason, and I have the student on top, so that's the 30, the way I set mine up.
Isn't that the actual?
That's the ratio.
Okay.
The actual number of students is 1,200. But I don't actually know my actual number of teachers, agreed? So I've got 1,200 students. How many teachers do I have right now? Because that's what I'm going to find. I'm going to have to find my actual number of teachers before I can find my new teachers I need to hire. So if I cross multiply, I have 30x equals 1,200. Right? And dividing by 30. What is my actual number of teachers in the building at the moment? There's 40. I have 40 teachers. So this is what I have right now. But I don't want a teacher-student ratio of 1 to 30. I want it to be 1 to 25, right? Same 1,200 students. That's not changing. I'll use a different variable here because it is representing a different thing. I want to know how many teachers I want to have, so I'll use y. And we'll cross multiply same as before. Now I have 25y equals 1,200. So what is 1,200 divided by 25? So this is also a number of teachers. But the question asked me how many additional teachers must be hired. 8. I would need 8 new hires, or 8 new teachers if you prefer. Is that good? Mary. Mary is working with measurements and writes up the following proportion. 12 inches over 1 foot equals 5 feet over 60 inches. How would you help her? You wouldn't necessarily. The issue is not about helping her solve something. It's about helping her know whether she did it right or wrong. Well, she could have. Yeah. Okay, so yeah, and that's actually the part you and I addressed earlier, isn't it? So the problem right now is that the inches are on a diagonal together instead of being either lined up vertically or horizontally. Do you guys see that? So when we were lining everything up earlier, and Michaela even asked me this question about how much sort of work, structure around it do we need? And the answer is you don't have to have the structure, but it sometimes helps to keep things in the same order. So the reality is that she's got some good things going on here, okay? So one of the things I like for you to recognize when students are doing work is that she's got an error, and that's true. But does she have anything that we could build on to say, hey, you had a really good start? Did she do anything right?
She put like 12 inches are in 1 foot, 6 inches are in 5 feet.
Yeah.
She just didn't put the...
Yeah, so each individual ratio is correct, right? The ratio on the left is correct. 12 inches is in fact 1 foot, and 5 feet is in fact 60 inches. So her individual ratios are right. Good job on the individual ratios. The problem is that her units are not in the same location when she compares the two ratios. So her comparison of the ratios are reversed. So one way to fix that would be that she could leave the left-hand side as it is She's comparing on the left-hand side inches on top to feet on bottom, and she could switch it. So this is 60 inches on top and 5 feet on bottom, right? She could also change it so that she's comparing inches on the left-hand side and feet on the right-hand side. And somebody else mentioned that, maybe Danielle, that yes, you could switch it that way too. So she could set it up so that she has the inches being compared on one side. Oops, that was supposed to be 6. And the feet being compared on the other side. But again, the feet would have to go across from the actual inches value that they represent. So 1 foot on one side would correspond to the 12 inches on the other side. So there are a couple other ways that she could compare things. So she has the individual ratios okay. That is okay to leave the same if she wants to. But the comparison's order is off, right? It's off. Okay, one more question in this section we're going to look at. Amy. Amy's friends told her that the ratio of boys to girls in her classroom was 5 to 6. Amy was surprised that her class would have only 11 students. What would you tell her? You look like you want to say something, Annika.
It could also have 22 or 33.
Okay, so she could have 11 students. Or 22 students, 33 students, etc. So let's talk about where your 22, your 33 came from. How does that work still with her 5 to 6 ratio?
It's a multiple of 11.
Okay, so if you have 11 students, it was 5, what do we have? Boys to girls? So 5 boys to 6 girls. That's the ratio. But the ratio might be reduced from the actual numbers of girls and boys, right? So she could have 10 boys and 12 girls. And if she did, that the reduced ratio is still 5 to 6. Right? Yeah. Or, you know, it could be, what did I have first? 5? I could have 15 boys and 18 girls. Again, still a 5 to 6 ratio. Could she have 11 students? Is that a possibility? She could. There's environments that you can teach in where your class sizes are more along those lines. If you're in a special education classroom, that's one in the public school system. If you were at a private school, my daughter was in a class at a private school once that had only 6 kids in it. So there are situations where the 11 might actually be the right number, but it's not the only possibility. Does that make sense? Okay, so here's what we're going to do. We have 5 minutes left, but that's not enough time to actually make any progress with group work. So here's what we're going to do. I would like for you to do the homework over the weekend, okay? Just save the group work. We'll do the group work, and we'll do review when we come to class on Monday. You have a test on Wednesday. Yeah, I know it's coming up. Zach Johns over in the Success Center has actually contacted me. He'll be letting me know at some point very soon when your review session ends. It's probably Tuesday night, but it could be Monday night, so just stay tuned for an email from him very soon. So we'll do the group work in class because we have not done any group work in class yet with all the crazy stuff going on. And we will do the homework before you get here. I'll start with homework questions. That way you have a chance to ask them since you won't see me again in a classroom before the test. All right? Have a wonderful weekend.